Here's a wild thought experiment for you. Is there a problem out there that no computer, not your laptop, not a supercomputer, not even some impossibly advanced alien machine a million years from now, could ever solve? Not because we're not smart enough yet, but because it's mathematically impossible? The answer is yes. And today we're going to meet the guy who proved it, decades before the first real computer was even built. We're talking about Alan Turing, the Turing machine, and one of the strangest, most mind-bending ideas in all of computer science, the unsolvable problem. Let's get into it. So here's what we're covering today. First, we're going to meet Alan Turing, who he was and why he basically invented the theoretical foundation of every computer you've ever used before computers existed. Then we're going to build a Turing machine together, piece by piece. It's way simpler than it sounds, I promise. From there, we'll talk about what it means for something to be computable at all. This is computability theory. And we'll work our way up to the big finale. A real, honest-to-goodness function that no algorithm can ever compute. Not, we haven't figured it out yet. Literally, never, ever, for any algorithm, ever. By the end, you'll understand one of the deepest ideas in computer science, and you'll have a story to tell at parties. Let's go. Let's start with the human story, because honestly, it's incredible. Alan Turing was born in London in 1912. As a kid, he was the type who'd get totally absorbed in puzzles and numbers. Not exactly a star student in everything, but a genius when something caught his interest. He ended up studying mathematics at Cambridge, and that's where things start getting interesting. In 1936, when Turing was just 24, he wrote a paper that would quietly change the world. At the time, mathematicians were arguing about a deep philosophical question. Is there a single mechanical method, a step-by-step procedure that could, in principle, solve any mathematical problem you threw at it? This was called the decision problem, and some of the greatest minds in math were obsessed with it. Turing's approach was brilliant. Instead of trying to answer the question directly, he first asked, "Okay, but what do we even mean by a mechanical procedure? Let's nail that down first." And to do that, he imagined a simple, almost absurdly simple, hypothetical machine. We now call it the Turing machine. We'll build one together in a minute, but the short version is, this imaginary machine became the mathematical definition of what does it mean to compute something. It's the yardstick against which every computer, every programming language, every algorithm is measured, even today. Now here's the part of Turing's story that gets really dramatic. Fast forward to World War II. Turing worked at a secret British facility called Bletchley Park, where he was part of the team that cracked the German Enigma code, the encryption system the Nazis used for military communications. Historians estimate this work shortened the war by years and saved countless lives. This wasn't abstract math anymore. This was Turing's theoretical ideas getting turned into actual code-breaking machines, some of the first real computers in history. And yet, and this is the part of the story that's genuinely heartbreaking, Turing's life ended in tragedy. He was gay, which was criminalized in Britain at the time, and in 1952 he was prosecuted for it. He died in 1954 at just 41 years old. It wasn't until 2009 that the British government formally apologized, and in 2013 he received a posthumous royal pardon. Today, he's recognized as one of the founding figures of computer science. The field's most prestigious award, the Turing Award, is named after him. It's basically the Nobel Prize of Computing. So, keep that name in your head. Turing machine. Because everything else we talk about today builds on this one idea from a 24-year-old in 1936. Imagine an infinitely long strip of tape, like an old cassette tape, divided into little squares. These are called cells. Each cell can hold one symbol. Let's just say it can hold either a 0, a 1, or be blank. Now imagine a little read/write head sitting over one cell of this tape. This head can do exactly three things. Read whatever symbol is in the current cell. Write a new symbol into that cell, erasing whatever was there. Move one cell to the left or one cell to the right. That's it. That's the entire machine, physically speaking. But here's where the brain comes in. The machine also has a state. Think of it like a mood or a mode it's currently in. And it follows a set of rules, basically a giant lookup table that says, if you're in state A and you read a 0, then write a 1, move right, and switch to state B. Rules like that. The machine just keeps following these rules, step by step, reading, writing, moving, and changing states until it reaches a special halt state. And then it stops. Now here's the mind-blowing part. This ridiculously simple setup, a tape, a head, and a table of rules, is exactly as powerful as any computer ever built or ever theorized. Your laptop, with its billions of transistors and gigabytes of memory, in terms of what it can compute, it's no more powerful than this little tape machine. It might be a gazillion times faster, sure, but in terms of which problems it can solve, they're equivalent. This idea is so important it has a name, the Church-Turing thesis. It basically says, anything that can be computed at all by any reasonable definition of computation can be computed by a Turing machine. It's not a mathematical proof. It's more like a deeply held belief that's never been disproven. And it's the foundation of computer science. So if Turing machines are this universal yardstick, where does your everyday programming language fit in? Here's the cool thing. Pretty much every general-purpose programming language, Python, Java, C++, whatever, is what we call Turing complete. That's a fancy way of saying anything a Turing machine can compute, that language can compute too, assuming you give it unlimited memory and time. And vice versa. Anything you can write in Python, you could in principle translate into a description of a Turing machine. This is actually a really useful, practical idea. It means that arguments about computability don't depend on which language you're using. If something is impossible for a Turing machine, it's impossible for Python, impossible for JavaScript, impossible for that quantum computer scientists are building in a lab somewhere. Well, mostly, quantum computing changes the speed equation, but not the fundamental can it be done at all question, which is a whole separate rabbit hole. So when computer scientists prove something is uncomputable, they're not just saying current technology can't do it. They're saying no possible technology built on the principles of step-by-step computation could ever do it. That's a profound difference. And that brings us to the big question. Let's get precise. A function, in the math sense, is just a rule that takes some input and produces an output. Like, take a number, double it. That's a function. Input, 5, output, 10. A function is called computable if there exists some algorithm, some step-by-step procedure, some Turing machine, that, given any valid input, will eventually produce the correct output. Notice the word eventually. The algorithm doesn't need to be fast. It could take longer than the age of the universe. As long as it's guaranteed to finish and give you the right answer, the function is computable. Most functions you've ever dealt with are computable. Addition? Computable. Sorting a list? Computable. Finding the largest prime? Less than a million? Computable. Just brute force check every number. Slow, but it works, and it finishes. So, is everything computable? I mean, it kind of feels like it should be, right? If you can describe a problem clearly, surely you can write some program, even a horribly inefficient one, that eventually grinds out the answer. This is where Turing dropped the mic. Here's the setup. Imagine you write a program. Sometimes programs get stuck. Infinite loops, recursive functions that never bottom out, that kind of thing. As a programmer, wouldn't it be amazing to have a tool that could look at any program, plus its input, and tell you, instantly and correctly, yep, this will finish eventually, or nope, this will run forever. This hypothetical tool is called a solution to the halting problem. And Turing proved, back in 1936, that this tool cannot exist. Not, we haven't built it yet. It is logically impossible for such a program to exist. Ever. For any computer. Let's walk through why. Because the proof is genuinely beautiful. And it uses a trick you've probably seen before without realizing it. Imagine, just for the sake of argument, that someone did build this magical program. Let's call it Halt Checker. You feed Halt Checker two things, a program P and an input for that program. Halt Checker analyzes them and outputs either halts, meaning P will eventually finish, or loops forever, meaning it never will. And crucially, Halt Checker itself always finishes and gives you a correct answer. That's the whole point of it. Now, here's the sneaky part. Let's build a new program called Troublemaker. Troublemaker works like this. It takes a program P as input. It feeds P, using itself as the input, yeah, a program analyzing itself, stick with me, into Halt Checker. If Halt Checker says P halts, then Troublemaker deliberately goes into an infinite loop. If Halt Checker says P loops forever, then Troublemaker immediately halts. Basically, Troublemaker is designed to do the opposite of whatever Halt Checker predicts. Now, for the killer question, what happens when we run Troublemaker and feed it itself? Think about it carefully. If Halt Checker predicts that Troublemaker, fed itself, halts, then by Troublemaker's own rules, it goes into an infinite loop. So the prediction was wrong. If Halt Checker predicts that Troublemaker, fed itself, loops forever, then by Troublemaker's own rules, it immediately halts. So the prediction was wrong. Either way, Halt Checker gets it wrong. But we assumed Halt Checker was always correct. Contradiction. The only way out of this contradiction is to admit that our original assumption was false. Halt Checker cannot exist. No algorithm can look at an arbitrary program and its input and always correctly determine whether it halts. This is the halting problem, and it's the most famous example of a non-computable function. The function does program P halt on input I is a perfectly well-defined function. Every program either halts or doesn't. There's a definite true-false answer for every case. But there is no algorithm that computes this function for all possible inputs. This might feel like a weird, abstract party trick, like a magic show where you can't figure out the trick, but it doesn't really matter in real life. But it actually has huge practical implications. Think about software bugs. We've all wished for a tool that could just look at our code and say, hey, this loop is never going to end. You've got a bug. The halting problem tells us a perfect general-purpose version of that tool is mathematically impossible. That's part of why debugging is hard, why automated testing can never catch everything, and why software verification is its own deep field of research. Tools exist that catch many bugs, in many specific situations. But a tool that catches all possible infinite loop bugs in all possible programs? Provably impossible. This connects to computability theory more broadly, the study of which problems can be solved by computation and which can't. It turns out the halting problem isn't alone. There's actually a whole zoo of other non-computable problems, and many of them can be shown to be impossible using the exact same trick we just used. Assume a solution exists. Build a troublemaker that contradicts it. Watch the universe break. Conclude the solution can't exist. This technique even has a name. It's a form of diagonalization, and it traces all the way back to a mathematician named Georg Cantor, who used a similar trick to prove there are different sizes of infinity. Turing basically took Cantor's idea and pointed it at computer programs. Let's make all of this more concrete with some examples and a simple mental visualization. Example 1. A super simple Turing machine. Let's say we want to build a Turing machine that takes a string of ones on the tape and just adds one more one to the end, like increment by 1, but in unary, where the number 3 is written as 111. Here's the tape, starting with 3 ones, 111 underscore underscore underscore. The rules might be state scanning. If you read a 1, move right. Stay in scanning. State scanning. If you read a blank, write a 1, move right, switch to state, halt. So the head scoots right, 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 past all 3 ones, hits a blank, writes a new one, and stops. Tape now reads 1111 underscore underscore underscore. We just added 1. It's almost embarrassingly simple, right? But Turing's genius insight was that you can build up from rules this simple, combining them, chaining them, nesting them, to eventually represent literally any computation. Multiplication, sorting algorithms, web browsers, video games, all of it, in principle, reducible to read symbol, write symbol, move left or right, change state. It's like discovering that every Lego castle ever built, no matter how elaborate, is made from the same handful of basic brick shapes. Example 2. The self-referencing trick in everyday terms. The halting problem proof felt abstract, so let's ground it with something more familiar. The classic liar's paradox. You've probably heard a version of this. This sentence is false. Think about it. If the sentence is true, then what it says must be accurate, meaning it really is false. Contradiction. But if the sentence is false, then what it claims, that it's false, is actually true. Also a contradiction. The sentence can't be consistently true or false. Our troublemaker program is doing the exact same dance, just with computer programs instead of sentences. If halt checker says I halt, I won't. If it says I won't halt, I will. It's a program built specifically to make any predictor about it wrong, just like the liar's sentence is built to make any truth value about it wrong. Example 3. A real-world analogy. The perfect lie detector. Here's another way to think about it. Imagine someone claims they've built a perfect lie detector, a machine that, hooked up to anyone, will correctly say truth or lie for anything that person says. Now imagine you walk up to this machine, get hooked up, and say, this machine will say, I am lying right now. If the machine says truth, well, then you are lying, since you said it'll call you a liar, and it just said you're telling the truth. But if you're lying, the statement, this machine will say I'm lying, is false, meaning the machine should have said lie. Contradiction. If the machine says lie, then your statement, the machine will say I'm lying, turns out to be true. But the machine just said, "You're lying." Contradiction again. No matter what the perfect lie detector outputs, it's wrong, just like halt checker. This is the heartbeat of computability theory. Certain kinds of self-reference create situations where no consistent answer can exist. And that's not a limitation of our cleverness. It's baked into logic itself. Visualizing the zoo of problems. Here's a way to picture the landscape of all possible problems. Imagine a massive Venn diagram. The biggest circle contains all possible well-defined problems, things with clear, definite yes, no, or input-output answers. Inside that, there's a smaller circle. Computable problems, the ones some Turing machine can solve. Turing's discovery is that this smaller circle does not cover the whole big circle. There's a region outside the computable circle, but still inside well-defined problems. Problems with clear, definite answers that no algorithm ever can compute. The halting problem lives in that outer region, and it turns out that outer region isn't just one lonely problem, it's actually enormous, way bigger than the computable region. In a weird, almost philosophical sense, things computers can solve is actually a tiny island in a vast ocean of things that are true but unprovable by computation. Okay, let's pull this all together. Alan Turing, in 1936, while still in his 20s, invented a simple theoretical machine, the Turing machine, to formally define what it means to compute something. Decades later, he helped crack Nazi Germany's Enigma code during World War II, becoming one of history's most important and most tragically treated figures. Turing machines are absurdly simple, just a tape, a read/write head, and a table of rules. Yet the Church Turing thesis says they're equivalent in power to any computer that could ever be built. This is why modern programming languages are called Turing complete. They can all compute exactly the same set of things, just at different speeds. A function is computable if some algorithm can always eventually produce its correct answer. But Turing proved that the halting problem, will this program ever finish running, is not computable. Using a clever self-referential trick, build a program that does the opposite of whatever a hypothetical halt checker predicts about itself, we get a contradiction no matter what, proving no such universal checker can exist. This isn't just a fun puzzle. It tells us there are hard mathematical limits to what computers can ever do, no matter how advanced they get. And that's computability theory in a nutshell, mapping out the boundary between what's computable and what isn't. If your brain feels a little stretched right now, good. That means it's working. This is one of those ideas that gets more interesting the longer you sit with it. Drop a comment if you want me to dig into other non-computable problems, or do a deeper dive into Turing's life. There's so much more to his story. Hit subscribe, like the video if this helped, and I'll catch you in the next one.